So I had the idea that I would talk about the scheduler, or about scheduling. No, this doesn't work. So there's some stuff happened in the scheduling country, and I thought it's like a good idea to bring everybody up to date. You are supposed to all know it, as with everything. And you commonly find this attitude like, well, you should very well already know this because you are working with so or so, or you studied so and so. But let's assume you don't know all of these things. And those of you who didn't know it, you can just like pretend that you knew it all along. So, but I'm something of a kernel generalist, and most people working in the kernel are experts, and as you know, an expert is somebody who knows more and more about less and less until they know everything about nothing. And a generalist, conversely, a generalist is somebody who knows more and more about, less and less about more and more until they know nothing about everything. So I'm right there, I know nothing about everything. So you're gonna see like some amateur talk about the scheduler. I've run into the scheduler now and then in my career. And well, it's a bit like, you know, people say that they know Rome, for example. Like, and that can mean different things. Like, yeah, do you know Rome? Yeah, I know Rome. I read Asterix, this like comic. Okay, of course I know what Rome is. So, okay, yeah, but that's pretty different from actually having, you know, visited. And I know Rome. I've been there. I've been at, you know, Forum Romanum, Colosseum. I've seen it. Like, I know Rome. Yeah, but do you really know Rome if you have done that? Now, if you have lived there or studied there, or if you were born there, that's a different thing. And that's the same thing with the scheduler. So everybody knows about the scheduler one way or the other. But there are very few Romans who actually work with the scheduler, or nowadays quite few people actually. But let's say, like, first, you can also not do scheduling. Scheduling has been around for a while, and I'm going to tell you where it started. But you can also like not do it. And some of these old operating systems, that's Atari TOS. If Atari TOS is actually scheduling, you have to beat me up after this. I think it doesn't. But Windows 3 is not scheduling, for example. It's just like, it's a loop. It's calling out to the applications and making sure stuff happens. The systems can feel very interactive, though they are not scheduling. There's no one-to-one between that. The Quantal Paint box here from the 80s, it's not scheduling at all, but it feels super interactive. It's like an early version of Premiere or Photoshop Premiere thing that they used for TV effects back in the day. And it feels very interactive, but that's because the cursor and the hardware and everything you do with the system is hardware. Like, the cursor moves by itself. It's not code. It's a piece of hardware that's just connected to that tablet, and things work that way and feels interactive. There's no scheduling going on. It's just a single-threaded application. And most microcontrollers and so on, if you work with them, you know they are not really scheduling unless they have a real-time operating system on them. So there is always the option to not schedule things. But if you want to schedule, scheduling started back there, 1961, 62. 1961, let's say, you have the compatible time-sharing system. And that's pretty much where scheduling became a concept that everybody doing computer science has to be aware of. Well, computer science started in 1936, but not in the form and shape that we know it today. And I usually use this slide for the computer students when they start university to introduce them to computer science, computer engineering, and software engineering, like where this concept starts. So in that picture, scheduling as a principle of computer engineering starts in 1961 with the Burroughs B5000 machine. And well, some people think that it's just silly when I bring historical perspectives to things, and other people just love it. I'm neither. I think it's just kind of important to get perspective. Perspective is one of those things that I always fall back to. for all kinds of reasons. An example of perspective would be like, I think I'm a bad parent, or something like this. Well, you have to put that into perspective. Maybe you're not cooking all of the food for your child yourself, and so on. Like, you feel bad about it, and you feel like you're just stressing through life. But then, there's this other guy downtown, Lund, who first went to this Calvin Knatet, where his daughter was running there, and that picture of that daughter is in a police investigation, because right after that he went home and killed a guy in his apartment with a hammer. And that gives you perspective what it means to be a bad parent. The blood was all over the kids' clothes and everything. It was completely horrible. So if you have perspective, you get things a little bit. You don't worry so much. And that apply. Maybe this was a stupid example, but that also applies to computer science. That the more perspective you have, the better your understanding is. At least in my opinion. So if you know this, you know all of these guys, right? I'm sorry, there are no women, but that's David Hilbert and Bertrand Russell up there to the left, and there's John von Neumann and Kurt Gödel and Alan Turing, of course, Erik Stemme, Peter Naur, and all of them you should be familiar with. Otherwise, we can next year take my 2-hour lecture on Swedish computer history, which I ran with the Computer Association. I think some of you guys up here have seen it, right? Yeah. And so we can do that if you feel that you need this full perspective. But today, let's focus on the perspective for scheduling, and that starts in 1961. It starts with this machine, the compatible time-sharing system. I love that picture of this guy sitting here. I use the swelling biceps and everything. I think it's what the Americans call a jock. I think this is just like one of those really popular guys who play American football, and he just goes into the university. I think it's Carnegie Mellon or somewhere where they are working with this, and he's just hammering away at this terminal. I just love that picture, that contrast with that guy. And this system here, over here, that's an IBM machine, I think. That was one of the first times that they deployed the concept of using terminals simultaneously. Several people would use a computer simultaneously from a terminal. And to be able to do that, you have to sort of multiplex through them. Go from this terminal to that one, read this one, input, output, work with the system, and so on. So that's where it started. But to give you a picture about how hard that must have been, this was pretty much Windows 3.0, because they didn't have this. They didn't have the hardware in the Burroughs 5000 from 1961. And why would that matter? Burroughs 5000, to give you some background, that's an Algol machine. The people who invented it were all young engineers. They were in their 20s, early 30s, and they just yeah, of course, we need to make a computer for Algol, because the Algol is the new important thing. A little bit like people think right now about Rust. So they adopted the hardware to the language, and Algol has this thing which is recursive, called by name semantics. So you need some way to you need to do recursion, all right? And how do you do recursion? Well, you all studied computer science, so you know that you do recursion by you put some values in the register. Let's put the state of the basic block on the stack, and let's call back into the basic block. Simple, right? No stack. Okay, so this machine has no stack. And no interrupts. Well, how the hell did they do it? I don't know. Probably it wasn't pretty. But this machine, the thing they did with it was that they invented stack, and they invented return from interrupt, basically, so that the hardware can store the state of the machine, including all of the status registers and so on, to a stack. They invented the stack. And then it can be pulled back with the return from interrupt instruction. That's pretty useful. We kind of take it for granted, but it didn't exist before 1961. So you can imagine what the computers before 1961 were to program. No stack, no interrupts, no return from interrupt. Maybe they had interrupts, but like no returning from them. So this was kind of revolutionary. And it's not only that, this is also a symmetric multiprocessing system for some definition of. It does have like processor 1 and processor 2. So it was also first with that in 1961. We might think about it like something recent, but it isn't. That's a very good article in the History of Computing, Volume 9, Number 1, 1987, about this machine. You can read it. So all right, you have return from interrupt, then you can do scheduling. At least the modern idea of scheduling. I don't know what scheduling would look like before you have a stack and a return from interrupt. How do you switch between contexts? No. I guess you like store it in memory somehow from a hard offset. You can probably do it. But scheduling, as we think about it in the kernel today, is something that happens on a timeline, and there's a time where it should schedule, and there's a time where it has to be scheduled. That's for some task. And what is a task then? Luckily, we have a definition of what a task is. In Linux, usually what we call a task is something that we schedule. It can be a process, it can be a kernel process, kernel thread, it can be a thread inside a process. And the only difference between these three different things is essentially which memory context it has. All the kernel threads naturally share the memory context and the MMU table of the kernel, something we call swapper page directory, because, yeah, we will talk about process 0. And in user space, you have processes and threads, and the threads, the only difference from a process is that it shares the MMU context with the process that it's inside. So if you schedule all of the threads in a process after each other, that's a good idea, because then you don't need to change the MMU table, and that's going to be more efficient, for example. So those are that's what we call a task. All of these things, that's a superclass of those things. Tasks, that's what we schedule. You heard this like multitasking and this stuff. And the way it practically happens is that there is a tick in the kernel, that's an interrupt that's occurring from a timer at an semi-even interval. When the system is up and running and all busy, it occurs at a fixed interval, which is something like 1000 hertz, 200 hertz, some cases, depends, you can configure it. And it issues what we call a scheduler tick. Most operating systems do something like this. And if this interrupt comes to the conclusion that the current process has used up its time slice, then it sets a flag in the process that is called the thread information flag need resched. So the process needs to be rescheduled. It doesn't reschedule. This is one of the common misconceptions. The timer tick does not change the memory context or everything. It could at the end of it, but it's not part of the tick itself. The tick only sets this flag and says, like, you used up your time, I'm lining you up for preemption. So preemption is what we call it when a task is replaced by another task. Also very general concept. Now, the place where things actually happen is at the end of a return from exception, from any exception. We call a function called schedule. And then schedule checks this flag, and if that flag is set, then we call into the scheduler. So at the end of some interrupt, and it sort of selects a new process to schedule at the return of the next exception or interrupt. So it says check and switch context, and that means it's sort of switches the current MMU table, it switches the global variable called current, which process is running right now, and then it returns. It doesn't go into executing that thing whatsoever, because you're still in some kind of exception here, or you're doing something else. Schedule can be called like at a random place in the kernel, like a hard loop or something like this, and then nothing happens. The only place where something actually happens is when you return from an interrupt. And at the end of an interrupt, you can return to what you were interrupted from, process X, or you can return somewhere else. That's the real trick. So that's how a preemption actually happens. You return from an interrupt. And that's like a little bit weird. Like where did we start out? Like when we start the kernel, we start something we call task 0 or PID 0. It's a hard-coded process. Well, you know, probably you are aware about that most processes in Linux and any other POSIX starts from a fork, like that you make a copy of the current context and then you replace stuff. And that's, well, somebody has to go first, right? So how do you solve that problem? Well, you hard code a process into the kernel, which is just like a struct in the memory. And that's PID 0. And that one starts, and then it sort of, initialize all of the device drivers in the entire kernel, and it goes to a point where it says, while one do idle. And there it just like takes down the system. That's the only task it has. So that's what happens with that process 0. It just do idle. It used to be called a swapper, I think, because it used to be like that swapping was in this process, and that's why the MMU table for the PID 0 is called swapper pgdir, swapper page directory. But we have since moved swapping into a kernel daemon, so that one is a little bit inappropriately named now. But the only thing, the first context of execution, the first assembly instruction you run, the only thing it really does in the end is sitting and idling, doing nothing, or trying to do nothing as well as it can. And it's just, while we don't need to reschedule, we test if we need to reschedule for the task, and in that case, well, when you return from some interrupt, it will another task will be scheduled in than this one. Otherwise, you try to idle the CPU. Now, why doesn't it hang there forever? Why is an interrupt? So something wakes it up, and then it rehashes the loop, and it goes back all the way up to the while one. So the kernel essentially sits in this loop forever, and it gets interrupted, and other things get scheduled in. So that's how we do it. Then the other trick that people usually are not entirely aware of is because how do you start a process? Where do you begin? For example, on ARM, there is no way to switch the current context. Like there's a bit in the system register that says supervisor mode, and of course, when you bring up the system, you are in supervisor mode. So how do I get to user mode? There is no instruction or anything like that. Well, what you do is you kind of cheat. On the stack, you populate a stack record with all of the registers and the program counter and the status register, and you return from interrupt. So whenever a process actually starts on Linux, in most architectures, not all, maybe not System 390, but most of them, what they do is like, I was just interrupted, let's start. That's the secret. Like, it is like it has come to my attention that not everybody is aware of this. We pretend that we are returning from an interrupt. That's how we start the process. And that's how it always has been, actually. So that you need to be aware of. And then we go into some Linux specifics here. We have a few preemption models. So what I said is like, yeah, you set this flag, it needs to be rescheduled. TIFF need resched. Does it mean that things will be rescheduled? We will do it when we think it's reasonable to do so. What I talked about was preemptible kernel mostly, like when you return from any interrupt, you can go into another execution context. But you can put no forced preemption. What happens if you do that? Yeah, when you call schedule, it will not time out your time slice, essentially. It will let you run to completion. So if you're running a process, you will get interrupted by the timer tick and other interrupts, yes. But you will get back to your execution context, the memory context will not be switched, and you will run that process until it yields or until it's hanging on a mutex or something like this. So it will just go on until it's finished with its business. It can terminate, it can hang on a mutex, or it can call somehow schedule explicitly and say like, yeah, I'm done here. But otherwise it will run to completion. And for servers, that's sometimes completely acceptable because you just want to put the workload and you don't really care which thing goes first. You just want it to do the work as efficiently as it can. And it could be the best scheduling policy. But it's kind of starting to feel a bit off these days because you just don't think like that. Then we have voluntary kernel preemption. That means that the kernel can at some point say like, it's okay if you preempt me here. And yeah, that's a bit Windows. That's like how things used to work in old graphical operating systems. But the thing that we mostly use these days is actually preemptible kernel or the scheduler control preemption model. This is called sched lazy. So preemptible kernel is like, yeah, but the timer tick can interrupt you. When you call schedule, if you have used up your time slice, if you have used up your allotted time, then another process will be scheduled in, and you will switch to that process at the end of the next interrupt, at the end of the next exception. This scheduler control preemption or lazy preemption is mainly a thing that has been added for some architectures, not all support them, but some architectures to improve real-time use cases mostly. So, and then we have the fully preemptible kernel real-time switch as well, which activates the preemption patch. Like do things maybe not as efficiently as they could be done, but with lower latency and meeting deadlines. So those are the config options you have. These days, with the stock kernel, you will have probably this or this if you're working on a laptop or so. Even servers, I think, have started to have preemptible kernels. Then we have the scheduling policies. Like how do we schedule? It used to look a bit like that in the bad old days with the System 5. And that's how some old people think about scheduling, that it's something with run queues here to the right. This is the symbol of a queue from queue theory. And you have the different processes there on the different levels. And well, it tended to look like all of the shells are on 0, for example, unless you have changed the priority with nice. And there are some special daemons and so on running on high priorities and some less important stuff running on low priorities. And for example, when Linux started out, it had what we call the ordo-n scheduler. So it was essentially a mute spin lock. And then you went over all of the processes and it looked at the goodness value, and that one had the highest goodness value would get scheduled next. And there were some heuristics to set this goodness value. It was just like a big array of processes. Not very civilized. And the time quanta and so on wasn't very much thought over. It was just like it had some relation to this nice value, but it wasn't proportional to it or anything. And after that, we had something we called the ordo-1 scheduler, which was a better version of the same, and then we accumulated a lot of kludges on top of it. So it started to like pay a little bit more respect to these different priority values. But everything we talk about here, we just currently batch under this name, sched normal, because we also have different classes. And that's the pyramid you see there to the left. So to complicate things, we have a number of different scheduler classes. most things that you do on a normal shell or whatever is in the sched normal group. So it's normal process. But then you can do not normal stuff. Of course, you can put something like low priority here, batch or idle, background tasks, cron jobs, whatever. And then you have real-time schedulers, round robin, and FIFO. Well, those are just exactly what you learned in computer science. That's usually the scheduler principle you learn about. And it's fine like, to just make a system using nothing but sched-RR at least. That's fine. That means sched-RR means that if you have several real-time processes on 0 here, for example, they get rotated with a time quanta if there are several processes competing about the same priority. Sched FIFO, on the other hand, means like once you are scheduled, you run to completion. Otherwise, you will not yield to anyone else. And on top of these scheduling principles, we have deadline. And that one is not even using priorities, it's using periodicity and a time quanta. So you get a certain allotment of time per period of computing. So you need a certain MIPS throughput, let's say. That's what the sched deadline scheduler does. It's a more civilized way of asking for a number of cycles for your real-time sound daemon or something like this. And it will take precedence over everything. But there's also a hidden one inside the kernel called the stop class. And that's what we use when we have to, for example, take a deadline task on one CPU core and move it to another core. We have to have a higher priority than deadline. So the stop class trumps everything, but it's also kernel, just a kernel internal thing. It's just used for task migration, more or less. So we have that hierarchy of different scheduling principles. Most of it is using the EEVDF scheduler, earliest eligible virtual deadline first. And we will talk about what that is in a moment. We were using the order 1 scheduler written by Molnar Ingo for until 2007. And it was getting kludgier and kludgier, and there was a lot of debate and strain, and people were shouting at each other in the scheduling sub-community, and it was all over Linux Weekly News and so on. They were passionate about it, of course. That's the reason why they paid so much attention. But a lot of debate pertaining to another scheduler developer called Konkolivas, and very colorful language, all of the usual, and input from different scheduler maintainers. The most persistent scheduler maintainer, Molnar Ingo, went and wrote what is called a completely fair scheduler, weighted fair queuing scheduler. The way this, and we just he or Torvalds just replaced it overnight. He merged the code. So what this scheduler that was used for 17 years, whatever it is, that one at least has some kind of theoretical idea about what it is doing, and some has thought through like the data structures and so on a little bit, or thought through. It was debated through. We have this social process. You have all seen it. But the basic idea comes from, I think, from network scheduling, really. You have different weights to different schedulable entities. P1 through Pn here are processes, and they have weights W1 through Wn. And then you sum these up, and according to weight, they get their allotted time on quantum wheel, let's say. So the idea is that if you have a pie like that, you slice the pie into sectors that correspond to your allotted time, and or to your weight. And since nice values in Linux or POSIX are negative, if they are bigger, you get a higher weight if you have a bigger weight if you have a negative nice value, a default weight if you have 0, and and so on, like a smaller weight if you have a positive nice value. So we actually, at this point, the nice values in Linux started to mean something. Before that, it was just like a pile of heuristics. A little bit like, yeah, if you have a negative nice value, or if you have the negativest nice value, maybe I will run you first, unless I don't feel like it. But after this, there is actually some accounting and some slicing that is kind of, we're trying to do the right thing. So you would account for every process, how much time you have used up in nanoseconds. There would be a structure to things that is ordered in a red-black tree like this. And yeah, why do we use a red-black tree? That's a good question. Anybody has the answer? It's a self-sorting tree structure. So for a key, you will always find the biggest key in the bottom left node. In this case, it's the red node and it's empty there. So when you put back, or when you update the needs to run value, I usually call it like the needs to run value, like how urgent is it for me to run in the CFS scheduler. Let's say for a process here, when these nodes will start switching, and the structure will be ordered afterwards. If it's the most urgent one, it will move down here, and it will be what you find in the bottom left of the structure. Maybe you've done red-black trees in computer science. It's a very nice data structure. It's hopeless to get it right, so I'm very happy that somebody has implemented it. But it's there in the kernel, and Ingo just used it, and yeah, it works. So when you call schedule, this current process will be accounted and things will move around here. And if the TIFF need resched flag is set, when schedule is called, it will switch the current process to the one which is here to the bottom left. And at the exit of the next exception, it will be scheduled. So you will return into that process. That's what's going to happen. And yeah, the weights actually mean something. Yay. And it was like that for a number of years. Then we got latency problems. Well, first, let's say you're scheduling like this. It feels really interactive and stuff. Desktops get like fluent. You don't get very much tearing in your UI. Things feel like responsive and so on. Does it mean that we have latency under control? Can you say, like, for this process, this is like really latency sensitive? Please do this. Like, no, it cannot. The only reason things seem so smooth is because of this. Everything is sorted in accordance to needs to run soon order, and interactive tasks tend to be a little bit bursty, like this. Comes like that. So they have a tendency to use very little time, not get their allotment, and move over to the left. Because they have a high weight, but or zero weight at least, but they use very little time, so they very quickly go here, and stuff starts to feel interactively. Nice trick, just all smoke and mirrors. But it feels interactive, nice. This is when you see like how crude programming can be sometimes. I will come to another crude thing, which is about priority inheritance. But yeah, latency isn't the best, and the trick we do is just use another scheduler class. Just put the sound daemon as sched deadline or sched RR or something like this, the pulse audio, whatever you have. Put it in this, like, it will take precedence over everything else. As long as you don't put too much stuff up there, it's fine. It's gonna run first. The sound is gonna get through. It's not gonna get choppy. Yay! But it does sound a bit crude, doesn't it? Would be nice if the sound daemon was running with everything else. We got sooner or later, like somebody like my manager Vincent runs into this problem that, well, things latency isn't really what it should be. How can I do something like latency nice and say that, like, for this process I want a low latency, I don't care about like, well, I want some reasonable time of computation, of course, but like the important thing for me is latency. Not, I want to execute soon and often. I don't want to execute whenever the scheduler feels like it. All right, how do you do that? So what happened was like he proposed some patches, and we were starting to get the order 1 situation where we put kludges on kludges, and Peter more or less said like, yeah, no, you know, I have an idea. I read an article. He's one of those guys who actually go and read scientific articles about real-time things. Most of these articles are bad. I think Thomas is not here this year, but said like, well, he stopped reading them because there's so many of them are just like written because I want to write an article so I can get my PhD. But believe it or not, it actually happens that some academics write an article and actually know what they are talking about and actually have a new idea. And those 2 guys had a new idea. This is Ion Stoica and his supervisor, Hussein Abdel Wahab. And they came up with a heuristic which was very interesting. It's called the earliest eligible virtual deadline first. And by now that's the scheduling policy we have put into the kernel. And it works a bit like this. We still have the processes and weights. So we have like some way to prioritize to begin with in accordance with the POSIX nice values and so on. That's fine. And then when we schedule, for every task, we have an allotted time, which is according to your weight, how much time you're allowed to take. And then you subtract the actual time you get through a revolution of the clock, let's say, how much quanta you actually get. You subtract that, so you can have a positive lag if you got too little time, and a negative lag if you got too much time. And then you sort your red, black tree in accordance with that. So you get this lag value sorted tree here. And only processes with a positive lag will be eligible to run over each iteration. And then you set the virtual deadline according to your weighted time allotment. So the eligible time is like the point in the future where the task will be eligible to run, when it's like you have been allotted time again, because you used so much time and now, well, you won't be allowed to run until here later on. And then a deadline where you are allowed to run from here, and there's your time slice, and it should be done by this point. And then, yeah, it just does the algorithm up there again, so you can rehash. Maybe you need some time for this. But accordance with the lag, you set an eligible time and an eligible deadline, and those vary for the task. So here are 2 tasks. There's task 1 and task 2, and it has an eligible time where it could start running and has a deadline by which it should. It doesn't. We are not saying must here because we are not doing real time, but a time where it should really encouragedly have been run. And you sort all of the tasks according to this, and then you take the earliest deadline first. So whatever is to the left, most left here, earliest deadline first scheduling you certainly know about. This is like an augmented earliest deadline first scheduler. So it uses this virtual time. These are the virtual times in the acronym. And then it takes the earliest deadline first and schedules that process. So how does latency come into this picture? Well, you take this allotted time slice and you chop it up in smaller pieces if you are latency sensitive, and say like you only get this first, and then you get this, and then get this. So what happens in practice on this timeline? If you start to give it smaller time quantas instead of giving like all of your time quanta at once, well, you still have all the same accounting for it and so on. Yeah, what happens if you take a smaller? Yeah, and then deadline moves over here. It gets run first. So the latency sensitive stuff gets run first. Neat. That was what Peter was thinking. I think that was what he was thinking. So by splitting up the allotted time slice into smaller pieces, it's like a little bit of a modification to that algorithm. Then the deadline moves over there, and it will be eligible earlier. So you can, if you have some tool to do that, like like latency nice, let's say, that sets like, yeah, well, let's take smaller increments. And then you will get your deadline pushed earlier, and you will get called the same amount of time, but more often. And you will get better latency for this task. So by doing this modification to the core scheduling, you can get nicer, better latencies in the kernel. So that's one of the big changes that happened. It happened 2 years ago. Was finalized not so long ago, maybe last year, end of last year. And now we moved over to this kind of scheduling. It's pretty neat. So you should be aware of that. This is how we do things now. There's a lot of old terminology and so on in the kernel, but this is how we do it. Another thing that we haven't addressed is priority inversion, which you have all heard about in your computer science classes, if you studied operating systems and scheduling. So, and what the story you heard is something like this. Priority inversion exists, but you always heard it in the context of a real-time scheduler with 99 priorities and priority inheritance. So the story goes like, just to repeat, what happens is like you have, let's say, 3 tasks, low priority, mid priority, high priority, and they compete about time. If there was no shared resource here, they would run the highest priority task, then you would run the medium priority task, and then you would run the low priority task. Okay. Right here, when we start out, the other 2 tasks don't exist, so we start running a low priority task. Then a mid priority task appears. Right before you started to execute that mid priority task, you took a mutex. A shared resource. What you mean with a shared resource in the Linux kernel is always a mutex. So you get preempted for a mid-priority task, no problem. You get preempted for a high-priority task, no problem. High-priority task takes that resource. Mutex lock. Okay, I can't keep on executing. Like the mutex locking is a preemption point. Then this sched need resched flag will be set, and you will be preempted. Okay, scheduler looks at the problem. Okay, he can't execute anymore. Let's run the mid-priority task. And that one runs. It can take 5 years, and then the low-priority task comes in, releases that shared resource, so that the high-priority task can execute again. And you immediately see the problem with this. But who cares? Really? So the usual solution to this is to say, like, yeah, we have 99 priorities. Let's just let this low priority task inherit the priority of the high priority task if they take the same mutex. So these data structures know about each other, and it's like, okay, I have both your priority. Low priority task gets scheduled here instead. Problem solved. The only problem with that is we don't have a 1 to 99 priorities real-time scheduler. We have CFS, or now we have EEVDF. What do we do? What do you think we do? We do nothing! Because we are not in this business. There were some patches in the real-time patch set. We just say to people, well, go and use the real-time scheduler then, if this is so important for you. That's pretty much what we say today. Well, it's not a good answer. So people have come up with a real solution. Like all of this, mostly it's John that's been driving this idea with proxy execution. There's a paper behind it. I haven't looked up the authors of that paper, but the idea is very straightforward. We have all of these data structures for scheduling, like with time accounting and allotment and weights and time quanta and your earliest deadline and your lag and your scheduling yourself in the EEVDF. Well, what about instead of this priority inheritance thing, we just pretended that the high priority task we get, we stumble on this mutex that is held by that low priority task. Well, let's just execute the low priority task and pretend we are the low priority task. So that's what this patch set does. It's not finalized, but it's going to be merged like soon. I hope it's on V17 now. And John is not giving up. So apparently, I think it will be merged. there has been some preparatory work where we split the scheduling into, or the task data structure more or less into execution context and a scheduling context. So where your time is accounted and where your execution time is accounted is two different things. Like I got so many cycles to run and so on, so your sysfs or procfs files are up to date. But then your scheduling context, where you actually get your time allotted, that's another thing. So when you run this masquerade, the time and the execution, the scheduling context you have is inherited from the high priority task. And this is actually like a very, it's a very interesting heuristic, because the place where it appeared is when you have deadline tasks. For example, it doesn't have like a priority, it doesn't have a weight. It has like a periodicity. So it's completely different from a CFS task or from a EEVDF task. And with this model, it doesn't really matter which scheduling class you have. You can be stop class, like you can be deadline, you can be real time. The only thing that matters is that this other lower priority thing will be run as if it was you, and the time it needs to run to its releasing that mutex is going to be accounted to you. You as you, the higher priority thing. And this patch set is V17, as I said. You can go and check it out on the kernel list, but I think it's going to be merged soon-ish. And it will be, then we actually have a priority, not priority, we have proxy execution in the kernel at that point. The place where this problem is not a problem for servers, though. It's not a problem for desktops even. It's a problem for Android. So Android, Google is driving this patch set. Yeah. But it's also deeply satisfying to solve this problem. Because the thing we did with ignoring it and telling people to just use real time or whatever, that's not really a good answer. So this has this like nice, yeah, it has this nice feature about it. And so far, like I have so far only talked about scheduling on one CPU. Just to inform you. Even on one CPU, we also have hierarchical scheduling. What hierarchical scheduling means is pretty much you have this is how you slice up your time to different tasks. If this little satellites were not here, this would just be the 4 different tasks running on the CPU. That would be fine. They would have this allotment, and so on. But you can put tasks into a group and schedule that entire group as if it was this slice in the scheduler. The scheduler data structure is actually hierarchical. It will be accounted the same time. This will boil down to the same, there's like a base timeline here, and this one has its own timeline, and that one has its own timeline, and so on. We just take a little bit more time of execution. There are several red back trees and everything. But it's hierarchical, and it works pretty much the same. Not everybody is using control groups, but most desktops and Androids and so on are using it, but just one level. Not like there's not a lot of people that put another control group in this now. It's just, that's a little bit too much. But you can do that. You can do it recursively if you want to. And then there's like this funky thing. Of course, people will do crazy things. Let's say that this slice is using the deadline scheduler class. So it's higher prioritized than everything else. It still has a slice, but it will get an accounting of its time and so on. But it will get priority over everything. And then inside of this little satellite, you have EEVDF. Yeah, you can do that. That's what they call a real-time server. So this one becomes a server, and the server itself gets a certain time of processing, but inside of that server, they are using the EEVDF scheduling. Does it work? Haven't tried it. There are people who use it. But you can do a little bit of advanced stuff there. So okay, so far we were only using one CPU. What happens if we use more? Which most of us do. This is a way I usually illustrate the SMP concept. Like up until like right before the 2000s or early 2000s, like the entire focus on the mass market for computers was uniprocessor systems. Like everybody had a PC on the desktop and it had one processor. There were servers that had several CPUs, but regular people and developers didn't know about them. And then when we ran into a brick wall with scaling, what appeared was symmetric multiprocessing. That wasn't a new concept. It was invented in 1961, as I said, on the B5000. But it came back from the historical archive. Perspective is good to have. Everybody could expect this to happen. But at the time, people were running workshops and everything all over the place about, like, how do we meet this new multi-core future? You mean the future that started in 1961? All right, yeah, I don't know. I think people have thought about it before. What about you go and read some old ACM articles? So, but it was portrayed as a new thing, and that's a case where perspective matters. I usually illustrate it like this, like one weightlifter who does all of, like, just as strong as possible. That's where, like, all your Pentium 5 or your, like, MMX, like, whatever you added in there to make the one single CPU stronger and stronger. And at one point, we all did body pump. So Ian and I go to this exercise. It means like everybody does the same thing with the appropriate weight. So this is actually heterogeneous multiprocessing here, if you should be picky. But the idea is if everybody was using the same weight and doing the same like exercise, they would be pulling equally the amount of weight. So you just split it up. And divide and conquer is another word that I heard, a phrase that I heard that also is possible to talk about here. And what we do for symmetric multiprocessing, let's say you have 2 cores, is essentially start to move processes across. This is from a Python tool I wrote that was called CG-Freak. It was actually done to investigate control groups, but I just had fun with it. So let's say like I print all of the tasks that are on one CPU and all of the tasks on that CPU along the edge. And then I write arrows as the tasks are migrated. How are the tasks migrated? They are migrated by a special kernel thread called the migration daemon. Oh, I think it is there, migration/1. And there's migration/0 here. You see that it's always the first process. And as I said earlier, that runs on the stop scheduler class. It trumps everything, deadline, whatever. And it just, so what happens when the CPUs are unbalanced is that this migration daemon comes in and says, I am the king of this country and I'm going to move you to another CPU. So it's a small computer program. It's not done inside of the scheduler per se because every CPU is scheduled separately. So every CPU has their own EEVDF tree, red-black tree, and scheduling. But then to even things out, we move things between different processors. So it's kind of independent, smart, right? That's a question. If the IPIs are increasing, it depends. It's a little bit of how long is a piece of string, is how small quantas do you set up, how much latency, nice things do you issue. Like if you put like small time quantas on everything, the things will be scheduled more often. There will be more preemption points, and schedule will be called more often. Migration, on the other hand, that's like happening more seldom. So that depends like on the data structures and everything. There are a bunch of heuristics around this. Like you typically try to, you prefer to move tasks on wake up when they have been like inactive, and then you wake up, then you like say, let's wake it up on another CPU core. That's the preferred mechanism. You can push them actively if like it gets really overloaded, but we try to avoid that, I think. I haven't looked at the algorithms really close, but that's pretty much how it works. But you can have if you just turn one CPU off, like all of the processes by way of the migration daemon will jump over, and all of the activity on that other core will stop, for example. Yeah. 5 minutes. All right. Well, I don't have so much more, so let's run the advanced stuff in 5 minutes. Well, it gets increasingly hand-wavy here because, like, yeah, now it's getting really complex. This is what like is the front line of scheduler development is about. Not this, but the next slide is going to be about that. We must first discuss the non-universal memory access situation, the NUMA, and it typically physically looks like that. That there are two CPUs like that, and each of them have their own memory. And well, even a 4-year-old can realize that, like, moving a process between two of the cores inside here is going to be cheaper than trying to move it over there. So what you do in the scheduler is that you have something called the scheduling domains. So it used to be like, well, all of the CPUs in that one CPU over there are in one domain, and all of those in the other one is there. And since they have their own MMU table and everything, it's really expensive to move processes across here, or tasks. So you associate it with a higher cost, so you do it only if you really have to. So if you start to get into a situation where one of those is getting really hot, like, then it start to get worth the cost to move things over to another CPU cluster. So that's a little bit how it works. That's what scheduling domains are about. It doesn't really affect you if you don't do NUMA, and most servers and things don't do NUMA. There have been some, but oh, most do it. This is super micro server, like this is what you have there. Oh, okay then. All right then. And it gets worse. Oh yeah. All right. So scheduling domains you have, but what was used to be in the bottom of this is. There used to be something called hyperthreading. It's not so popular anymore. And hyperthreading means that there is an even lower cost of moving threads between. Usually there were like 2 hyperthreads on a single core. And the idea is like you use the same compute units, but you have 2 different queues of instruction decoding and so on. But the same cache and the same ALU. So moving a process between 2 different hyperthreads is something that's really, really cheap. So that would be like 5 cents or something. But hyperthreading is not so popular these days because of security. I think people have to turn it off because they are so insecure. But yeah, Ian has a lot of these NUMA machines apparently. So, and those of us who work in the mobile space, we have run into this thing that we have been working on the latest years, which is when you run into really complex situation. Let's say like you have a CPU cluster that looks like that. There are 2 small CPUs and 2 big ones. They have more computing power. They have the same instruction set. They can run the same code. It's not about that. They are just more performant. And on top of that, they can also choose different operating points, different frequencies. So that one is more performant, and it also has a higher, can also go to a higher frequency than that one. And as you see, like when I put the task here, it gets smaller, and when I put it here, it gets like slightly bigger because of the performance characteristics of the different CPUs. And well, how do you migrate for this? Like, where should I put stuff? Well, I can put it here, or if I put it over there, or I'm not going to bump into a high. If I put it there, I'm going to go up in frequency, and it's going to consume more power, and I'm on a mobile phone. Like, that's not good. Okay. Can I move all of the tasks over here? Will that result in lower power being spent? Or if I move them all over here and run to race to completion, so that since it's so quick, it will soon get the work done, and I can move everything over there and go slowly and so on. Like, what do I do? What's the good solution? There's a question over there. Yeah, I think they have it in firmware there. Though recently they have started to look at this scheduler. So yeah, what is the right decision? So it's actually a little bit up in the air, but what we have developed, or the community has developed, is the energy-aware scheduler. So the kernel has an energy model, an EM, that can define how much power something will consume, like a CPU, or some other device, DMA, whatever. And using these operating points and some physical characteristics of these different CPUs, they are put into that energy model. And then we have what we call PELT, I think, per entity load tracking. So we are able to compute for that task. Like if I put it here, what will the effect be on the energy model? Or if I put it here, what will the effect be? So I test it in all different combinations, and I see like which one is cheapest. Where will I save the most energy? And then I put it there. And as you probably understand, that's kind of a costly operation. That's a lot of maths involved. So we only do that at task wake up, not random preemption. But recently it has come to some people's attention that we might actually need to do a bit of push and pull with this, and push tasks actively over for this reason. This is only really used on heterogeneous systems like that. This was first appeared on the big. LITTLE architecture for ARM. And what we did first, like we get this problem, what shall we do? We just like, yeah, let's put all of the processes here or here to begin with, and just turn the other one off. And when we don't use so much of those, so they would fit there, they just turn them off and move everything over there. We just did suspend and resume, essentially. That's what we call the big. LITTLE switcher. Then later on, the energy awareness scheduler came about. And then the front line of development is around this, because that heuristic is not finished. Still working on it, still hashing it out. And then there is Morten from ARM presented another problem, which is, yeah, what if you have even more complex things than this? Let's say there's a shared computation unit between these two, or between these two. So it actually is better to move things over there, because that shared computation unit is taken by a task running here, so it's not a good idea to put it up there. We have no solution to that. It's just on the map. That's like things that are coming. And I'm out of time. If there are any final questions? Good timing, right? Just one apparent error that I didn't know about NUMA on servers. Yes?
Are you aware of any architectures where it's already solved the Linus kernel problem where one of those heterogeneous processes doesn't support certain instructions and throws an exception? So you detect, for example, OpenSSL detects essentially, I can do NUMA, and then the spread gets scheduled on another port, and then it says like exception.
Yeah, that's unsolved. It would be nice if those of you who have this problem become scheduler developers and help us solve this problem. As you probably have understood by now, it's not like super simple. So with that, I hope you all now understand how we do scheduling and in Linux and so on. So let's welcome the next speaker, which is Kevin.